Hello class, welcome back to 2.1. So I brought back the last page because I just wanted to recap really quick what we've learned. So what we've learned is that minimum and maximums in the graph of a function are really important, right? That's the turning points in the graph. Regardless of if you have the intercepts, you know where a graph starts and ends, how will we weave through it, right? And also, how high do we have to go before we turn the graph back around? So what we've learned is that if you want to find a local minimum or maximums, what you need to do is look for where the derivative is equal to 0 or it's undefined, right? Because at any min and max, either you have a horizontal tangent line or you could turn the graph in a sharp corner, but then there's no derivative there, okay? So the question becomes though, okay, we've found, right, we went through the process and we know how to find critical points, and look at this, this problem had 3 of them. It doesn't tell us though if they're minimums or maximums, yes? So that would be important as well. So how could we tell that? Let's pick this minimum point, for example. What must happen to the graph to reach a minimum point? Well, the graph first has to come down, right, and then go up. There's another minimum point. The graph comes down, afterwards goes up. Comes down to the minimum, it goes up. So, of course, for a maximum, we're going from going up to going down. So basically what happens for either a min or a maximum, the function has to change directions, right? From decreasing to increasing, decreasing, increasing, and so on and so on. So that's exactly what this next theorem is telling us. What does it mean for function to be increasing and decreasing? I was saying earlier, goes up, goes down. Those are the fancy names for goes up and goes down, right? So the proper definition is a function is increasing on an interval, means that if it means the y values get larger, as the x's get larger, the y values get larger, right? So that's really your y1 is less than y2. So the y's go up as the x's move to the right. And a function's decreasing means the what? The y's are getting smaller, right? From a larger y, we're going down to a smaller y, right? As the x's move to the right, okay? Now, how can we tell if a function's increasing or decreasing? Super, super easy. The first derivative not only takes care of critical points, right? Possible mins and maximums, but it also tells you where a function's increasing or decreasing. So it says a function's increasing if and only if the derivative of that function is greater than 0. Greater than 0 means positive, right? So if you have a positive derivative for all the x's in that interval. So here's an interval, and here's a function that is increasing, yes? So what happened? It's going up. What happens with the derivative? Again, remember the derivative is measured by the slope of the tangent line. So what can you tell me about the slopes of all these lines? All the tangent lines go up, right? So they all have positive slopes. So the slope is the derivative of the function, right? So hence, that's all you have to do is if a derivative is positive, that means the function was heading up. And it doesn't matter how it's heading up, right? How it's curving up. The point is, if you draw a tangent line at any point here, those tangent lines go up, so their slopes are positive. Okay, whereas what? Of course, a function's decreasing if as you move from left to right, right? We're now looking at a graph this way, always moving from smaller to larger values, from left to right on the number line. What happens with these tangent lines? All the tangent lines seem to be decreasing, right? Going down. So these all will have negative slopes. In other words, negative derivative. Yes. And sure enough, if a function is constant, what does it mean constant? It's horizontal graph. Yes. So if a function is horizontal, then all the tangent lines are horizontal, right? For the whole interval, right? So that means all the slopes are equal to 0. Okay. All right, so we're going to put this right away to good use. And continue on the talk. So this is going to be a big problem for you guys to solve. How do we use the first derivative in order to properly graph this function? Okay, so the important part is what I'm going to teach you is how to make a sign diagram. Okay, so you read the book. Okay, well, anyways, when you read the book, the examples in the book are going a little bit beyond or a little bit further, and there's a lot of explanation. Professor can put a lot of X's and arrows and really a lot of work to make those sign diagrams in the book. What I'm going to do is I'm just going to simplify it for you. They don't have to be so involved for you to figure out how the graph of this function is going to go. So all I'm telling you is that the book goes a little bit above and beyond to what you actually need to do in order to figure this out. Okay, so pay attention. All right. Use the information about the first derivative of the function to make a sign diagram for the first derivative and use it to graph the function. So the first things first, well, let's find the first derivative. So that's the first step, find the derivative. Okay, well, that's a 3x squared. And by the way, we already found it. So good thing is we don't need to waste more time. It's on 2 pages before, right? We found already the critical points. So, but again, what are the steps? I'm just going to write it here. Find the first derivative. The second thing, find the critical points, right? How do you find critical points? Set the first derivative equal to 0 or see where it is undefined. And again, it's becoming undefined if you ever should have a fraction with x's on the bottom, yes? So we already did this, and we already found the critical points. You're finding the critical numbers first. I'm going back to our problem. We're finding first, remember, the critical numbers, yes, by setting the derivative equal to 0. Then we plug in into the function to find the y values as well. So we did find the critical numbers. Let me write the critical numbers first. They were x equals to 1 and x equals to -1/3. Okay. All right. The next step would be what? Make that sign diagram. And that's what I'm going to show you. And a sign diagram better will have some signs. In other words, pluses and minuses. Okay, so that's what I'm going to do next for you. I'm going to make a sign diagram for the first derivative. And that's how it looks like. You're making basically a table. Okay. At the top, we're going to put x. Underneath, we're going to put the derivative. And at the very bottom, we're going to put the function. Okay. All right. So our x's, of course, go from -infinity to +infinity. Yes? So in other words, I'm going to graph this function on its whole domain. And this being a polynomial function, it's going to graph from negative to +infinity. In between these two values, we found 2 numbers of interest, right? The critical numbers. That's where things are happening in your derivative. So you better place these in order as they would come on the number line. So you're not putting 1 and then -1/3 because that's not the order on the number line. First comes -infinity, then -1/3, then 1, then +infinity. Great. So what do you know about your first derivative at these points? You know that the first derivative was 0, right? That's how we found them. We set it equal to 0. We solved it. Not going to solve it again. We already did in this section. But we know they're 0. What we want is we want to figure out the sign of this first derivative in between. 0 has no sign. Yes, it's neither positive nor negative. So all you have to do is think about a test point in between these values. So in other words, here, let me pick what's a number between negative infinity and negative 1/3. How about negative 1? Yes. So plug in negative 1 here into the first derivative and see what values you get. So 3 times negative 1 squared, that's a 3. Negative 2 times negative 1, that's a positive 2. So far 3 plus 2 is 5. Minus 1 more is 4. So all I care is that I get a positive value. Yes. Now let's move on and pick another. We call these test points in between. So if you plug in a 0, that's a value between negative 1/3 and 1, by the way, into this derivative function, what are you going to get? You're going to get that the derivative, again, it's about the derivative, not the function, that's why I plug it into the derivative, is a negative, yes? And then plug in a 2, because 2 fits between 1 and infinity. So 3 times 4 is 12, minus 2 times 3 is 4, so 12 minus 4 is 8, minus 1, that's a 7. So all I care about is that it's a positive. So, of course, you might have picked 5. You might have picked any other point in between. Now, so what kind of conclusions can we draw about the function itself from this? Just as we saw on the previous page, where the derivative is a positive, the function must be increasing. So I'm just going to draw an arrow up. Where the derivative is 0, what happens to your function? It evens out, right? So a 0 derivative means a horizontal tangent line. Yes, so the graph evens out. Negative derivative means the graph is going to go down. 0 means it's going to even out. And positive means it's going to go up. So what we found from just the sign diagram is that what? At negative 1/3, we're going to have a maximum point, yes? At positive 1, we're going to have a minimum point because the graph first goes up, down, and then back up again. So we already know the shape of this graph. That's it. So the last part of it will be to, and again, you already found the critical points here because we already found them in the previous steps, but honestly, we will just find the critical numbers first. So let me maybe even do that. Find the critical numbers where the derivatives, these are your critical numbers. And then at the end, you're going to make a table of values from the important points. In other words, find the y's. Let me show you. So what I'm going to do next is which points are of interest in my function, because that's what I'm supposed to do, graph the function, yes? So which points are of interest? Negative 1/3, positive 1. So at negative 1/3, let me go back to the previous page. At negative 1/3, we found the answer to be 59/27. If you put this in your calculator, that's about 2 point something. At 1, the y value was 1. So again, in section 2.3, we're going to take this further and we're going to find the second derivative and the inflection point. So at the very end, you put together a table of values for those important points in your graph. For now, if you want, you can put in more values. If anything, 0 is always easy to plug in. It's an additional point that will guide you through and give you more clues of what happens to the function. So by the way, it's easy to find, right? F of 0 is 2. And again, this is a table for f of x. It's done. So let me graph this for you. There isn't much room for the graphing part. And it's surely, yeah, it's going to be to scale. That's good. These numbers aren't much. So what important points did I find? I'm just going to put a 1, 2, 3 here. A 1, 2, 3. Negative 1, negative 2, negative 3. Okay, so let me plot these points I found. So I found that negative 1/3, which is about here, goes with something that's a little bit more than 2. 2 point, again, I don't know, 2.1, something like that. 1 goes with 1. 0 goes with 2. And that's about enough. So how does this graph go? And again, another issue would be you could find the x-axis intercepts with the tools that you have learned in college algebra. But again, the purpose of this course right now is to take you further, finding those intercepts. If you do remember those Descartes rule of signs, possible rational zeros, it takes a long time to basically solve this equation to find the intercept. So we're not going to do that. We're just going to concentrate on this newfound freedom in finding or in being able to graph the function. So what do we know? We know that the function first does what? It goes up until it reaches this x value of negative 1/3, yes? Then what happens at negative 1/3? It turns and it's going to start to go down. It's going to go down actually through this x and y-intercept, which totally makes sense, yes? And it's going to go down until it reaches what? An x of 1, which is right here. And then it's going to head back up. Okay, that's it. That's your graph. So there was one intercept that we couldn't find. And we can, but we're not going to spend the time. So what do we find? This point here is a local min. This point here was a local max. So in other words, we know how far down we have to go before we turn the graph around. So before, when you even only could find the intercepts, you only knew that this is going to go through here and somehow through here. So if anything, maybe you would have just made the graph go like that. So definitely it looks way different. So these turning points are huge, hugely important for the graph of a function. All right, let's try this again. We'll do the same thing over. So what we're going to do is find the derivative because we want to find the critical numbers, yes? And same thing, we already found that. We did set the derivative equal to 0 and we solved it. And we found that those critical numbers are 0, 2, and negative 2. Again, we found it 2 pages ago, so we're not going to waste time. Okay, found the critical numbers. What do I do with the critical numbers? I'm going to make myself a sign diagram. X, f prime of x, that's a sign diagram for the first derivative, and we're going to draw conclusions about our function based on this. So, which points am I going to put up here? I'm going to put anywhere from negative infinity to positive infinity, and they come in this order. Negative 2, 0, and then positive 2. Yes? Great. So we know at these points, whoops, let me do green. At these points, the derivative is equal to 0. I need to find the signs in between. So I'm going to start right here at a negative 3, let's say, and I'm going to plug into the first derivative. So 4 times negative 27, let's see, let me put this in my calculator. As a matter of fact, I think I already had it, so you guys can put this in your calculator. Whatever it is, put it in your calculator. I did find already that this is going to give me a negative value, okay? Pick a number between negative 2 and 0. Oh, let me show you something else. Why did I figure this out so much faster? Because when we factored this some pages ago, this factored form actually helps way better, even with the plugging in part. So we factored it, we set it equal to 0, and then we found these 3 answers, remember? So why would it be helpful when you plug in a negative, when we plug in any of these values? So when you plug in a negative 3, 4 times negative 3 is going to be a negative. Negative 3 minus 2 is a negative 5, that's a negative. And negative 3 plus 2 is negative 1, which is negative. So 3 negatives definitely is a negative. Now let's pick a number between negative 2 and 0. Let's say negative 1. 4 times -1 is a negative. -1 minus 2 is a negative. But -1 plus 2 is a positive. So 2 negatives times a positive make a positive answer. And by the way, I can teach you this trick as well, that the signs will come alternating. And you really don't have to waste your time to plug in so many values. That feels like, I mean, doesn't take that long, especially if you plug it into the factored form. But the same thing, as soon as you plugged in one value, and of course, which one would be easiest to plug in? 0, right? The one in between here. You figured out this is negative, so the signs left and right have to be alternating positive, okay? The only time when the signs don't alternate is when one of your factors comes with an even power. So if I should have an x minus 2 squared, the derivative or the expression does not change signs left and right of 2. We'll see an example like that. But you factored it, you see each factor is linear, the signs are alternating. Okay, so what conclusions do we draw about the function itself? Negative derivative means the graph is going down. Then it evens out, it's increasing, evens out, decreasing, evens out, increasing again. So that's how my graph is going to go. Down, up, down, up. Okay. Now all I have to do before I graph it is I have to find some points. Yes, I have to know, okay, fine, I know where the x is, but what's the y value to it, right? Where on the xy plane will I find that point? So I'm going to make a table of values here for my function. And we already did, in fact, we did find those critical points. And we plugged in -2 goes with -13. 0 goes with 3, and 2 also goes with -13. Great. So now let's graph this function. Okay, so we know that these are the important points I have. 0, 3, 2, 2, -13, and -2, -13. By the way, you don't have to keep the same units on the x and the y-axis. So if these are the ones on the y-axis, the ones on the x-axis could be way larger. It doesn't matter, but fine. I kept it consistent. You don't have to, though. Okay, so what happens to the graph? First, the graph goes down, yes? It goes down until it reaches this minimum value where x is -2, yes? Then the graph will go up until it reaches the value where x is 0. Then it goes down until it reaches the value where x was 2. Then it goes back up. So sure enough, 4 intercepts you would have been able to find out of this 4th degree equation. However, the turning points are really what we're concentrating on right now. There it is. Okay. What else? I have 2 more problems for you. And number 3, we also already have the derivative found. And the derivative was 2 over 3. And if I remember correctly, cube root of x plus 3. Remember that? We took the derivative. We did try to set it equal to 0 in the first video, but we figured out the only way a fraction is 0 is if the top is 0. But it's definitely undefined. It doesn't exist if what? X is -3. That's what makes the bottom 0. So the only critical number we have was -3, and they came from the fact that the function was undefined. The derivative was undefined. Okay. So here it is, the x, f prime of x, and f of x. Where are the x values? Oh, just kept rolling. Negative infinity to positive infinity, and -3 was my critical number. What do we know about the derivative at -3? We know that it's undefined. So I'm not going to put a 0. You can put a bar or you can write undefined. It's up to you. I'm just going to put a bar as in it doesn't exist. Okay. Let's pick some values though. And same thing. What I'm going to do is I'm going to pick a 0. So if we plug in a 0 for x, we have a 2 divided by 3. Cube root of 3 is positive. So definitely all this is going to be a positive value. You can even try and put in a -4 just for fun, but I'll tell you it's alternating. So -4 plus 3 is -1. Cube root of -1 is a negative times these positives that makes this negative. So what happens to the graph of the function based on this? A negative derivative means the graph goes down. A positive derivative means that the graph goes up. An undefined derivative, it doesn't mean it's going to even out. It's not going to come nicely horizontal. The derivative wasn't 0, right? So it's either a corner point, yes, or maybe a vertical tangent line, but we know it's a corner point. And then you will be asking yourselves just now, how do I know it's a corner point? You get vertical tangent lines in vertical asymptotes in a function if the initial function had already a fraction. But the initial function is defined. You can plug in, the domain of it is all real numbers. There's no stopping. Okay. The domain of this is all real numbers. You can plug in any value you want for x. So it's not like there's a break and then you have to jump over. So what we found that critical point, we plugged in -3 into this function, we got -5. Okay, so here's your only point of importance. -3, -5. And what do I know? I know the graph comes down to a corner and then it goes back up. Whoops. Yeah. Now I kind of drew it, but I could have made it even better. It doesn't go through 0, 0. This is what caught my eye. Because if I plug in a 0 here, I'm not going to get a 0. So if I wanted to make this definitely prettier, I should have picked a second point, one that's easy just to plug in. Now, the cube root of, or 3, right? 0 plus 3 is 3. 3 to the 2/3 is something I'd say about 1-ish, a little bit more than 1. So I'm guessing this is about 3 point something. So this graph, I'm going to make it better. It's actually going to cross here. Too bad I can't erase. So that's a better graph. Now, again, as I said, we're not really holding on to intercepts or anything like that. We really want to know how, where the graph is turning. Yes, so that would not be a big mistake because you did address the important facts we found from here. Of course, as I said, the more points you plot, the more accurate your graph is going to get. Now, why did I make the graph come down like this? Because I already know the graph is not going to do what? Have a nice horizontal tangent line. I already know that. There is no 0 derivative there. We have to come to a corner, yes? So to make it come to a corner, we're going to do something like that. Okay, you could make it this way, and it still comes to a corner. Surely it's not going to be a line. Okay, we already know that's not an absolute value function. The only thing that comes as a v is an absolute value function, that's for sure. Now, if you're wondering, definitely we're going to revisit this problem in 2.3 when we'll talk about the second derivative, and the second derivative will will address the problem of concavity. So a graph can come down this way or it can come down but this way. So it's a matter of concavity. I mentioned it to you in 1.5. So we'll definitely have a better clue once we add on this sign diagram for the second derivative. Okay, so almost there. I do want to finish on this video. What I want to do is, this is a problem we're starting completely from scratch. We haven't already found the critical numbers for this. So do the whole thing one more time. So the first part is find the derivative. Yes, I said. That's 3x squared minus 18x plus 27. Yes. The second thing is find the critical numbers. How do you do that? You set the first derivative equal to 0 if you can, right? And that's exactly what's going to happen. You can definitely solve this equation. This derivative will never be undefined because we don't have a fraction, right? A rational function with zeros on the bottom is what makes an expression undefined. So let me factor this some more. I factored out the greatest common factor of 3. Numbers are multiplied to 9 and add up to 6, or 3 and 3. So this time, as you see, there's only one value, one critical number, and that is x equals to 3. Great. Let's put it in a table. That's the only critical number, yes? Okay, let's see what happens to the first derivative. The first derivative is 0, yes? Now, let's plug in some values, left and right of 3. I can plug in 0. 0 is a value less than 3. So if I plug in a 0 in my first derivative, definitely I'm going to get a positive value, yes? You can put it in the factored form as I had suggested. 0 minus 3 is negative 3. Negative 3 again, two negatives multiply to a positive. Now, this time the signs are not going to alternate. Why not? Because as I said, if these factors come in squared, by the way, that's what happens, right? This is one common factor. So really, when you square something, it always is positive. Times 3 is always is positive. But here, let's plug in a 4. 4 minus 3 is 1. 4 minus 3 is 1 again, right? So it's the same factor twice. Either they're both negative or they both turn out to be positive. So the sign doesn't change left and right of 3, right? So it stays as a positive, okay? Plug in the 4 here if you don't believe me. You'll see that it stays positive, okay? So what happens to the function? Well, a positive derivative means the function's going up, yes? A 0 derivative means the function is going to nicely even out, yes? And what happens? It's a positive, well, I should have started it lower. It's positive again, so it's going to go even out, then come even further up. So it's not coming down, right? The derivative is always positive. That means the function's always increasing, okay? One more thing, I'm going to make that table of values for the function itself. And the only important point I found was 3. Plug it into the function, okay? So if you plug in a 3 there, you are going to get 31. I have that already. Maybe we should learn from our mistake and put in one more point. If I plug in a 0 just for fun, which is easy, into the function, yes? That's gonna, if I plug in a 0 into the function, that's gonna turn into a 4, right? Okay. Okay, so let's graph this thing. So I'm gonna have a 1, 2, and a 3. And I'm going to have to go to 31, so I don't want to go to 31, and so I'm going to go up by 10s. Okay, so here are the 2 points I found. If x is 0, y is 4. If x is 3, y is 31, so just about here, okay? So what do I know about this graph? I know it always goes up, yes? So I know the graph is coming up, 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 up. What happens at 3? It evens out, yes, so it almost becomes horizontal, as if it wanted to turn back down, yes? However, it's not going to turn back down, but it's going to keep going up. So it does what a cubic function does. If you remember the graph of y equals to x cubed, this you've learned in college algebra. It was one of your fancy functions, and the way that one looked like was that it was coming up towards 0, evening out, and then continuing. So that's exactly what's happening here. By the way, if you were to factor this, in fact, you would find the cubic x minus 3 cubed plus 4. Or plus, maybe not 4, plus 31. There you go. That's the cubic function. So thinking about transformations of the cubic function, you move it 3 units to the right, yes, and 31 units up. So it goes from the origin 3 to the right and 31 units up. So you just simply move that point in the middle. There you go. Okay. And I only knew to guess this simply from the graph of the function. I could read it. Okay, so that concludes 2.1. You will have plenty of these problems to practice for homework. It really does not take that much. It doesn't have to get that complicated if you just follow these steps we just followed. Find the derivative, set it equal to 0, find your critical numbers, put them in order on the number line, and then make a sign diagram for the first derivative. That's key, right? Positive, negative, 0. These clue you in on what happens to the function, right? Positive derivative means it goes up, right? If you have a negative derivative, it means it goes down. It's actually super, super easy. It doesn't take that long. So we don't have no min or max in this graph. Even though, as that's what I was saying before, just because you have a critical number or a critical point, it doesn't mean it has to turn into a minimum or a maximum, okay? So a critical number simply means something the derivative is 0 or undefined. You could find a min or max, but there's a perfect example where the derivative is 0, yet you don't have a min or a max, right? So just to complete this, that's a minimum value right here. Okay. All right. See you guys in 2.2.